So we already did problems number 1 and 2 from worksheet number 3. So we're going to start today with problem number 3. It says, in many locations, old abandoned stone quarries. So these are places where rocks have been dug up out of the ground and used for different things. Around here in Ohio, when you see stone quarries, usually they're going for limestone aggregate or gravel. But these have become filled with water once excavating has been completed. And here in Ohio, you know what we use them for? Scuba diving. Anyway. It always sounded like a terribly cold idea to me. But anyway, while standing on a quarry wall, a boy tosses a piece of granite into the water below. If he throws the rock horizontally with a velocity of 3 meters per second and strikes the water 4.5 meters away, how high above the water is the wall? So the idea here is that we've got a quarry wall. Usually they're pretty straight. And there's water down here. And we've got a kid who's throwing rocks. And the rock gets thrown into the quarry. There we go. So what we need to do is figure out what we already know about horizontal and vertical motion, and then use that to solve some problems. So what we know is he throws a rock horizontally with a velocity of 3 meters per second. And so for horizontal things, we know that our velocity is 3.0 meters per second. And we know for vertical things that, let's see, we strike the water that's a horizontal thing, 4.5 meters away. So our change in horizontal position is 4.5 meters. And we're asked how high. So that's the thing that we need to solve for. We already know that acceleration due to gravity is minus 10 meters per second squared. And we know that our vertical velocity here is going to be equal to, our initial vertical velocity is going to be equal to 0 meters per second. And this velocity is our horizontal velocity. Now, we've got two pieces of information here about horizontal motion. And so that means that we can figure out what the time ought to be. So if we know time from the horizontal information, we can use that with the vertical information to figure out the vertical drop. So to solve for time, we need to know that our change in position is equal to velocity times time. So time is equal to our change in horizontal position divided by velocity. So we're going to be looking at 4.5 meters divided by 3.0 meters per second. And that's going to give us 1.5 seconds. That seems kind of far. Something falls for 1.5 seconds. Okay. So then to find the next thing, our displacement, what we have is acceleration, initial velocity, and time. So we're going to be looking at that parabolic equation again. 1/2 at squared plus initial velocity times time. This initial velocity piece is going to equal 0 because our initial velocity is 0. So we only have to worry about acceleration and time. So our height, our vertical displacement is going to be 1/2 times minus 10 meters per second squared times time squared, or 1.5. Sorry, whoops, I wrote meters and then seconds. Seconds squared. That looks terrible. Fix that up. So 1.5 seconds squared. Folks have been telling me lately that my 5s and my s's look too much alike. Okay. So 1.5 times 1.5, my calculator gives me 2.25 times minus 10 divided by 2. So I got a height of minus 11.25. The negative makes sense because our rock is falling downwards, right? He's not throwing this upward and it's hitting the water at the bottom of the quarry. He's throwing it downward. So it should be minus 11.25 meters. How'd you guys do? Okay? That was pretty straightforward, I think. You guys have any questions about it? All right. Number 4. Tad drops a cherry pit out the car window 1 meter above the ground while traveling down the road at 18 meters per second. How far horizontally from the initial dropping point where the pit hit the ground? If the car continues to travel at the same speed, where will the car be in relation to the pit when it lands? Well, that last part is just like the airplane problem we did where the bottle got dropped out the window, right? And in that case, we said that the airplane would be directly above where the bottle hit the ground. I think the same thing would be true for our car here. All right, so what do we know? We know that our car is going down the road. I'm going to draw a very simple car so it doesn't get like in the way of my cherry pit drawing. Kind of looks like a train car, but that's okay. And there's windows in my car. And Tad, I'm going to assume that Tad is a kid. And Tad drops the cherry pit out the car window. 1 meter above the ground. And it's going to fall, right? So our car is traveling forward. Our cherry pit is going to drop in a parabolic fashion. So, it's a meter above the ground. We know that it's moving at 18 meters per second. So that's all the stuff that we know. All right, so vertical things. We know that our height here is 1 meter, so this thing is going to travel minus 1 meters. We know that our acceleration is minus 10 meters per second squared. We know that our initial vertical velocity is 0 meters per second squared. We could use that information to find the time, which is something that we may ultimately need to be doing. For horizontal stuff, we know that we are traveling with a horizontal velocity of 18 meters per second. We don't know time and we don't know distance because what we're being asked is how far is it going to travel. So that's what we need to find. So we are going to have to find time and then use that to solve for our distance. So we're going to be using our quadratic equation again. Again, our initial velocity is going to be 0, so we're not going to need this last term. Our height is minus 1 meters equals 1/2 times acceleration, which is minus 10 meters per second squared, times time squared, which we don't know. So our minus 1 meters equals minus 5 meters per second squared times time squared. So time squared equals 0.2 because it's going to be 1 divided by 5, so 1/5. 1/5 is 0.2. Second squared. Time is going to be the square root of that. So this is going to be, I got 0.45 seconds. So to find our distance, we're going to use our other equation, or our one equation for horizontal motion, is that the displacement is equal to the velocity times time. And that's what we want to know. So we're going to take our 18 meters per second times our 0.45 seconds. I got 8.05 meters. How'd you guys do on that one? Math part's okay. Okay. Just need to draw some motion maps back. All right. So next one says a kickoff sends a football with an initial velocity of 25 meters per second at an angle of 50 degrees above horizontal. What direction is that 25 meters per second? What do you guys do with that information? Okay, so imagine that our football, I'm going to draw a terrible kicker here. Oh, that leg has too many bends in it. There you go. All right, so our football gets kicked at an angle of 50 degrees above the horizontal. Okay, so there's my football kicker guy. You guys might know football better than me. He's going to be okay, I think, though. And here's what we're looking at. This football is getting kicked with a 50-degree angle above the horizontal, and that's where our 25 meters per second goes. Which means that we have to figure out the components of the velocity. So that's what this is asking about. Find the x and y components of the velocity. We want to figure out this velocity, velocity y, and this velocity, velocity x. In order to do that, we're going to need to use trig. Oh no. Should draw my triangles a little bit better here. There we go. So that means we're going to be using two triangles, just like we were doing before, to break these into components. And we need to find the horizontal side and the vertical side for this. So I don't know, if I wanted to find the vertical component, then I would say I would be looking at, let me see, this angle here would be 50 degrees. So I'd be looking at the opposite angle from 50. So the opposite and the hypotenuse would be the sine. So the sine of 50 degrees is equal to Vy over 25 meters per second. And so Vy equals 25 meters per second times the sine of 50 degrees. So I got 19.2 meters per second. You might have done this a different way and still gotten the right answer. You could have used the cosine of 40 degrees and gotten the same answer, and that's okay. For the other one, if I wanted to solve for Vx and use this adjacent side, then I could use the cosine of 50 degrees and say that that's equal to Vx divided by 25 meters per second. And Vx equals 25 meters per second times the cosine of 50 degrees. And so Vx would be at 16.1 meters per second. How'd you guys do on those? Does it make sense? Sometimes we have to figure out components. All right. Next, it asks us to find the time that the ball is in the air. So we're going to have to think through some things to be able to do this. To find the time the ball is in the air, we could use either horizontal stuff or vertical stuff to solve for that. For horizontal stuff, we know, do we know how far it went? We don't know that. All we know is that the horizontal velocity is this 16.1 meters per second. For vertical information, stuff that we know that the initial vertical velocity is 19.2 meters per second. We know that acceleration due to gravity is minus 10 meters per second squared. We don't know the height. We don't know the time. But we do know that if our football goes up in the air and then comes back down, that at this point in the middle, the velocity is going to be equal to 0 meters per second. So if we can find the time that it takes to get there, and then double that, then we can figure out how long the ball was in the air. Does that make sense? Okay, so if we do that, we're going to need our two velocities, acceleration and time. So I'm going to take a look at my page. Two velocities, acceleration and time. I think that this very first equation will work. So if we say our final vertical velocity is equal to our initial vertical velocity plus acceleration times time, and I want to solve for time, then I'm going to put in these values. I'm going to say my final velocity, because I'm looking for the velocity there at that point. It's going to be 0 meters per second is equal to 19.2 meters per second plus my minus 10 meters per second squared times time. I'm going to subtract 19.2 from both sides. So minus 19.2 meters per second equals minus 10 meters per second squared times time. I'm going to divide both sides by minus 10. I'm going to end up with 1.92 seconds equals time. So that's how long it takes to get to that middle point. So to get all the way to this point over here, I'm going to have to multiply that times 2. So the 2 times 19 or 1.92 is going to give us 3.84. So the thing to be careful of for making sure that you solve that one correctly is just understanding what this parabolic shape is going to look like and recognizing that you can solve for the time when the velocity is going to be equal to 0. I'm going to go ahead and write some of these things in here now. So I've got my time is 3.84 seconds. All right, find the horizontal distance that the ball travels before hitting the ground. Well, this for sure is going to be using our horizontal information and our equation. The change in x is equal to our velocity times time. So our velocity there is 16.1 meters per second. Our time is 3.84 seconds. I'm going to pull my calculator. Times 16.1. So I got 61.8 meters for that one. Add to my list. And the last thing is find the maximum height of the ball. So we're going to be looking for our delta y up here. With our initial velocity, acceleration, and time, we can use our parabolic equation from our cover page. So it's going to be 1/2 times minus 10 meters per second squared times our time squared, which is 3.84 seconds. Actually, if we do it that way, it's going to give us 0. So we're going to have to do this for the maximum point like we did here. We're going to use that information to solve this. So our time there is going to be I think 1.92 seconds. Plus the initial velocity, which is going to be, where'd it go? 19.2 meters per second times time 1.92 seconds. This one needs to be squared. So here I got minus 18.432. .84. So I've got a positive and a negative here, and both of these will have the units of meters. So I'm going to take that number minus 18.432. And I got 18.43 meters. Is that really high? Those of you who are in soccer and football. How many feet would that be? That's about 20 feet in the air. Is that a lot or is that a little? Anybody? It's 20 feet in the air a lot for basketball. It's like 4 people tall. That's a lot, right? That's the top of the gym. Okay. How'd you guys do on those? Okay? All right. So we have one last problem today. It says draw a 2-dimensional motion map for the velocities and another for the acceleration. So here's how we're going to do this. We're just going to sketch these out. Because we know, how many seconds does it take? This only took 3 seconds to land. So we're going to kind of just draw an imaginary one here just to kind of see what's going on. We're going to imagine it took a little bit longer, okay? So we know that we hit a peak at some point. I'm going to just draw a couple here. All right. Too steep. One for velocity, one for acceleration. So we know that these guys are only in the air for less than 4 seconds. And so it would really be something like one here, one here, one here, right? If we were drawing this accurately. There, there, there. But that really isn't going to tell us too much. So I'm going to just draw this with a couple of representative locations just so that we can kind of get an idea for what this ought to look like. So I'm going to imagine that it took exactly 4 seconds for it to hit the ground instead of 3 seconds. Okay, so I've got all of my dots in the same place on both of these motion maps. And the axes here are vertical position and horizontal position. I'm just going to label those with X's and Y's. X. Like that. Okay, so for our velocities, it asks for velocity X, velocity Y, and total velocity. So to do those, we're going to imagine that with this one, we know that our horizontal velocity is going to be constant. And so to make that about half the distance between my dots, I'm going to have an arrow that looks something like this. And those are all going to be equal. So I'm going to make that Vx. For my horizontal acceleration, I'm actually not going to have any. So I'm going to write acceleration in the x direction is equal to 0 meters per second squared. No. No horizontal acceleration. For my vertical velocity, right, with velocity, we're going to indicate that by the length of our arrow, and the length of our arrow should be halfway between 2 points. So if I imagine that this dot is extended over above my first dot, I only want to draw a vertical arrow that goes halfway there. I could do the same thing with my next dot, halfway. So what happened to my arrow? It got shorter, didn't it? So if we're getting a shorter arrow, that tells us that acceleration is opposite the direction of the motion. Does that make sense? So here that's telling us that our acceleration is in the opposite direction of motion, so it's downward. So down here, when I draw my acceleration arrows, I'm going to draw downward ones. And that makes sense because we know that on Earth, our acceleration in the y direction is equal to minus 10 meters per second squared. We also know that it is constant, so that no matter where we are in our motion, that's always going to be true. We expect it's going to be true on this side too. Up here, we have actually a, let's see, at our peak, our vertical velocity, so I put Vy there, so it's in the y direction. We know that it's 0 meters per second, so there's no arrow there. And then as our ball starts to descend and we start looking at what those arrows should be like, we can see that here we're going to have a downward arrow, and we would expect to have a downward arrow here as well. And if that arrow is lengthening in the negative direction, that tells us that we have a negative acceleration. So down here, just like we had predicted, we would expect that we would have arrows pointing downward, representing our acceleration due to gravity. Just wrote all over on top of my delta for delta x. So what questions do you guys have about that? Does that help make sense of what that should look like? This is a lot simpler too than the first one that we did. So when we talked about this the first time, um, we did something that looked like this. And the main difference here is that we only included horizontal and vertical components. For this one, it also mentions the overall velocity. So the overall velocity for these would be the sum of the two vectors for each point. And the way that you're going to want to do the sum is the same way. It's actually the reverse of us figuring out the components of a vector. You're going to add them together. And so what I would do if I were you, I would complete our rectangle. And then I haven't been labeling very well. Here's our VYs. Our VYs are vertical. Then our total is going to be the sum of the two. And what happens if you draw those well is that they end up looking like the shape of the parabola. Up here, we could add this with its horizontal vector. Remember the horizontal vector is 0? And so if we add this to the vertical vector is 0. And so if we add this horizontal vector to 0, what we find is that the total vector is equal to the horizontal vector. Do you guys have any questions about anything on that worksheet? No questions.